Today we're going to talk about the real world meaning of the area under the curve. It turns out the area under the curve is not just some kind of geometric thing. You know, in the real world, unless you're doing a very specific kind of a thing, you usually don't care about areas of curves of whatever. But actually the area under the curve, which is the same as the definite integral, actually has a lot of uses in the real world, and it's because of this relationship. The area under the curve is related to what we're going to call the total change. All right, this is sort of the interpretation as far as changes is the interpretation of the definite integral. You know, the derivative is the rate of change. What is the definite integral in terms of change of something or other? It is related. This is how it's related. The area under the curve, that is the definite integral, and the total change. Here's the relationship. This is sometimes called sometimes given a name. This is called the total change theorem. This is the relationship between the area under the curve of something and this thing called total change, which I'll say what that means. Anyway, the theorem says this. The area under the curve, this is the definite integral, but look at this prime here. Peep game on that prime, okay? If you're taking the area under the curve of the derivative of something, this is equal to the total change in f of x from a to b, all right? The total change in the original function, all right? So if you have the derivative, here's the derivative, this is the original function. If you take the area under the curve of the derivative, that is equal to the total change, the total amount that the original function changed from point A to point B, all right? This is called the total change theorem, and let's just talk through one specific example, and I want to try to convince you that this is really the case, all right? The area under the curve of the derivative is straight up equal to the total change of the original function. I want to cast your memory back for this example all the way back to the very first day of our class. We talked in somewhat vague terms about, we did some example about how fast you're growing over various points of your life, all right? I want to revisit that example. I'm just going to draw a little piece of a graph about that. Okay, here is a graph. This is related to that old how fast were you growing problem that or that example we did way back in the beginning. Let's imagine that this is a piece of my graph for the derivative. See the prime there? Okay, so this graph represents how fast I was growing in terms of inches per year. You can see the units there. How fast I was growing in terms of inches per year in each year of my life. So when I was 14, I was growing at a rate of 3 inches per year. On my 15th birthday here, I was growing faster, 4 inches per year. Then 16, I went back down to 3. Then 17, I went down to 2. All right. As usual, I don't know if this is realistic. I'm just making this up. But I want to know, what does the area under the curve of this derivative actually represent in the real world? What I told you before was that represents the total change in the original function, which would be my height, right? That would mean the total change in my height from, say, along this region. So I would like to know about this area right here. Let's focus on that area, right? This, as an integral, is the integral from 14 to 17 of f prime of t dt, right? This is the area under the curve of the derivative. And I would like to make the case, I'm trying to convince you, that this area is actually equal to the total change in my height from year 14 to year 16. So total change in height from year 14 to 17, right? That's what I'm trying to convince you of. Let's ask ourselves, now this area, we still haven't really talked about how to compute the area exactly. We've talked about various ways of estimating the area. Let's just look at this and draw the simplest one of those estimations, which would be estimating by rectangles on the left side, all right? There would be 3 rectangles here, and you could figure out what the areas of each of those are. Actually, it's easy to say. This one has area 3, this one has area 4, this one has area 3, right? And so this area the area from 14 to 17, f prime of t dt. This is approximately 3 plus 4 plus 3, which would be 10, right? I just added the areas. Remember, each time the area is the height times the base width. The width is each 1 each time. So that's the what this integral is, approximately. Does that have anything to do with the total change in my height? Well, let's think about it. You could ask yourself, in order to compute this, what is the total change in my height from year 14 to 17? Well, you could break it up into 3 years, right? You could talk about, all right, the first year, how much total did I grow in the first year? Well, say in year 14, I grew how much? Well, if you think about it, I was growing at the beginning of year 14, I was growing at 3 inches per year. So that's how fast I was growing per year, 3 inches. So that means in year 14, I grew, I suppose, approximately 3 inches. Now, if you look at the graph, you can see my growth actually accelerated throughout that year. So the true value is slightly greater than 3, but whatever, and as an approximation, 3 is pretty good. All right, what about the next year? In year 15, how many inches did I grow? Well, you look at the graph, you see in year 15, at the beginning at least, I was growing at a rate of 4 inches per year. So how many inches did I grow during that year? The answer is 4. So in year 15, I grew, I got 2 commas there. Serious about commas. Okay, in year 15, I grew approximately 4 inches. Now the true value is actually slightly less because my growth rate was slowing down throughout that year. But as an approximation, about 4 inches. And then in year 16, that is, 16 to 17, how many inches did I grow? Well, again, you look, at the beginning of that year, I was growing at a rate of 3 inches per year, so I grew approximately 3 inches. All right. In any case, what's the total change in my height from year 14 to 16? Well, the total change would be this plus this plus this. But I feel like you should feel in some way that I'm really saying the same stuff again, right? The same exact computation is what I'm doing here. It's exactly the same as these areas, right? Instead, so this 3 corresponds to this area 3. This 4 corresponds to this area 4. And remember, even when I said something like this 3 actually is only an approximation, in reality the value is slightly greater because of this increase. That's exactly the same as you could say this rectangle is only approximation to the area. In reality, the actual area is slightly greater because of this business when it goes up here, right? The fact that this is an approximation of the total change is exactly the same approximation that this is for the actual area under the curve, all right? What would you do if you wanted to make this approximation more accurate as far as the area under the curve? You would make additional rectangles. But if you wanted to make this judgment more accurate, you would say, instead of going year by year, let's go every 6 months, all right? And look at points every 6 months. That, again, is going to be the same as improving the estimate by rectangles by drawing more rectangles, okay? These two concepts, they're not different. Actually, they are entirely the same concept. So that's why I hope you're convinced by now. The area under the curve here is exactly the same as the total change in my height. That is not the derivative, but the original function. So in this case, these two things, or this one number, they are the same number, is about 10. You can get more accurate if you want by drawing more rectangles, but I didn't give you an equation, so it's hard to get any more accurate than that. All right, let's try a couple more examples. Okay, in this example, this again is a made-up problem. Let's say P of t is the population of my town. And this is a graph of P prime of t. That would be how fast the population is changing from year to year. So in year 0, what this means is in year 0, there is no change in the population. In year 1, the population was up by 100 people. In year 2, again, there was no change. In year 3, the population was down by 200 people. Year 4, again, down by 200 people. Year 5, the population did not change. In year 6 and beyond, the population increased again. What I would like you to do, your job, estimate the total change in the population of my town from year 0 to year 5. And I have to tell you more about your strategy here. I'm going to say using rectangles. well, actually, I mean 5 rectangles with the left endpoints. All right. Estimate the total change in the population. Okay, this is not a big deal. You just have to translate, as always, you have to translate this word problem description and figure out what exactly do you want to be computing. The answer is you want to be computing the area under the curve, because the total change in population is equal to the area under the curve, also known as the definite integral. In this case, we want to go integral from 0 to 5 of p prime of t dt, right? This is the answer. That is the total change. We're going to estimate that using 5 rectangles using the left endpoints. From here, it's just a straightforward, estimate the area under the curve using rectangles. And maybe we can just do it right down here. You need to look at the picture to do this, so I don't want to erase that. This estimate the area business, we begin by drawing a little chart of the interval that we care about, although it's already right here, but if you like, you can say, okay, I'm going from 0 to 5, and I got to break that into 5 pieces. 1, 2, 3, 4, 5. All right, you have to figure out, what's the b minus a, what's the delta x thing. In this case, it's pretty simple. The delta x is 1. That's the width of each interval. And so, using the left endpoints, that would be these guys. You just add them up as usual. So it's going to be the area under the curve, this thing, which is the total change. Maybe I'll write that for my answer. Total change is approximately equal to, I'm going to do the whole rectangles thing. So I'm going to add a bunch of stuff together. Each time it's going to be delta x times this thing plugged into the function. So it's going to be delta x, which is 1, times p prime of 0. I said prime because that is the function I'm talking about, is p prime, plus 1 times p prime of 1 plus blah, 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 plus 1 times p prime of 5 is what I want to see here. And then what are those numbers? How do you get these numbers? In this case, you don't have a formula to plug into. You just look on the picture. So this is, I'm not going to write 1 times every time. 0 here. P prime of 1 is 100, so 0 plus 100, plus P prime of 2 is 0, plus P prime of 3 is minus 200, plus P prime of 4 minus 200, plus P prime of 5 is 0. All right, and that's it. Actually, this one is not so hard to add together. You get negative 300. What does it mean that the answer is negative? Well, the total change from year 0 to year 5 is approximately 300 people left town. All right. That's that. Next, I want to do a real world problem. Check it out. All right, check this out. I got my iPod Touch here. Can you see that? I hope so. All right, this is kind of old, but I've got a little app there called Accelerometer Data. This is a 99-cent app. I bought this with my own money, stag money. I'm not getting reimbursed either. So I hope this works. Now, can you see the sliders here? What this thing does, your phone actually has a sensor in it called an accelerometer, which measures accelerations. And if you look carefully, you can see there are 3 values there, x, y, z, and they're all like jiggling around. They're more or less stable, but not quite. It's because my hand is moving the thing. This is actually how your phone or whatever it is detects if you're tilting the thing, or if you're, shaking it or whatever. If you want to play those fancy video games, doing the Donkey Kongs, your phone can tell if you're shaking or tilting or whatever. This is how it knows. Right now you can see the values of x and z are hovering around 0, while the y is measuring around -1. This is measuring the acceleration due to gravity in each of the 3 directions. So x will be left to right. Like, I don't know if you can tell, but when I do that, the value in the x direction goes crazy. Y is ups and downs, and z is sort of in and out of the screen. All right. So right now the y is measuring -1. That's because the ordinary force of gravity is pushing down on the phone, and the phone is registering -1 g. The units here are in g's, and g is the force of the Earth's gravity. All right, so 2 g's would be if you shove this thing down really fast at an acceleration which is equal to 2 times the force of gravity. Anyway, if I tilt it this way, you can see right now the y and the z are both at 0, but the x is at 1. That's because this, what is now down on the phone, is the positive x direction, the way it's being measured. All right. This is how your phone can tell if it's being held this way or being held this way. And you know, your phone automatically will sort of switch the display around or whatever. It reads the values from the accelerometer, and the accelerometer is measuring acceleration, which is due to gravity or due to you just, you know, shaking the thing around or whatever. All right. You can actually use the accelerometer to measure acceleration. If you want to find out, say, how fast your car can accelerate, you can actually, you know, put your phone in there and accelerate your car, and then read the data that comes out of the accelerometer, and you can, you know, tell how fast your car was accelerating. That's what this little app is for. You can actually save the accelerometer data and download it onto your computer, which can allow you to use your phone or whatever it is to do all kinds of science experiments involving acceleration. And that's what we're going to do in just a moment. Okay, we've got our accelerometer, which is going to measure how fast the thing is accelerating in various directions. So that's going to be able to give us like data, which can describe a function a of t. It's not going to be a formula. It's just going to be a bunch of numbers that describe the acceleration. Anyway, what can you do with the derivative? I mean, with the antiderivative, with the integral. Remember, a of t, the acceleration, is the derivative of the velocity, right? It is the how fast the velocity is changing. That's what the acceleration is. So we can find the total change in velocity is equal to the integral of the derivative of the velocity, but that's the acceleration, right, from, say, a to b. All right. What that means is you can use acceleration information to tell you the total change of velocity. So, for example, you can get in your car and accelerate by a certain amount, and by reading information from the accelerometer and doing the integral, you can figure out what your total change in velocity is. And in other words, if you start at rest and then you go a certain speed, you can figure out how fast you're going by looking at the integral of the acceleration. So that's what we're going to do. It's going to be awesome. I'm going to show, okay, got my iPod here. Put it on the swing. All right. Try to hold it so it stays on there. All right, go for it. You want to push to start? Yeah. All right. Is that as fast as you can go? Yeah, pump it. All right, here's what this looks like when you import this data into the computer. What you see here are a bunch of times, and then these are the 3 acceleration readings at that instant that we're reading on the accelerometer. You can see the one in the x, the y, and the z direction. All right, let's see, and I decided to graph these. There is the graph of these data points. Okay, you can see some pretty chaotic behavior here. This was probably as I was carrying the little thing over to the seat, and then I put it down on the seat, which probably happened around here. Right around here you can see some stability, like it wasn't moving very much, and then it started moving, probably when she started swinging. And then you can see in this area, you can see some actually fairly regular back and forth kind of motion. All right, it's actually fairly complicated, the physics involved in doing this, but this is what all that data looks like. Pretty cool, huh? I think so. Okay, so the data about the swinging is actually fairly complicated to do real physics or real analysis on that data because the swing is swinging. It's actually kind of rotating. It's not going all the way around, but it's doing part of a rotation. And if you really want to handle that, you have to do your physics using a rotating reference frame, which is actually very complicated. So I thought maybe we should do something a little simpler than that. what I did, I didn't make a video of myself doing this because it's not very interesting. What I did was I put my iPod on the floor in the elevator in the Banno building on campus. Here's a little reenactment, okay? Here's my iPod. This is what I did. I'll do it up here so you can see. And then I hit the button on the elevator, and the elevator, went up. It went up for a while, and then it stopped going up, right? And the doors open, and I walked out. Okay. Let's think about what would the acceleration read. What the acceleration reads right now when it's just sitting on my desk here. It's just flat acceleration, at least in the z direction. What do you expect the acceleration to look like? Well, it's basically going to be flat because think about when you're standing in an elevator, you don't actually feel anything. It just feels like you're sitting in a very small room. Except for 2 points, right? You feel something when the elevator starts to move. You feel a little boop. In fact, if you think about it, if you're going up in the elevator, when the elevator starts, you feel very slightly heavier for a moment, right? There's some acceleration when you go up. Right after that little bump, you feel normal while the elevator is in motion. But then when the elevator stops, you feel another bump that's kind of in the opposite direction, right? So at the beginning, if you're going up, you feel like a little heavier. And then the elevator goes, and then you feel a little lighter. So the graph of the acceleration that I expect to see is something like this. Right, where this is when I hit the button and the elevator started moving. There was some acceleration registered, and then nothing for a while, and then some acceleration registered in the opposite direction when the elevator stopped moving. This is the picture that you should expect to see when you look at the data. Let's check it out. All right, let's look at the data. Okay, here you see what I get when I download the accelerometer data. If you graph this, I made a graph of this, it looks like that, see? So you can see the downward bump and then the upward bump, which is exactly what we predicted right there. All right, this, I don't know what that is. Maybe that's when I picked the thing up, I don't know. That's just a weird little blip. Anyway, let's focus right on here, okay? This little region right here, this looks like about maybe 7.5 seconds to about 10 seconds, all right? I want to just zoom in on there and see if we can tell what was the total change in my velocity. This would be the same as just asking like how fast was the elevator moving once it started going, right? What was the total change in my velocity from here to here? This, of course, is a graph of the rate of change of the velocity. This is the acceleration, which is v prime. And so we can find the change in velocity by doing the integral across this region. So if you slide over here, what I did was I just picked out some of those numbers from this time, 7.68, which is right at the beginning of this blip, and then to the end here, 9.7, I judged the end of the blip over there. All right, so here are those times. Here are the accelerations from that first column over there. Remember, these are in G's. What I did first was I removed gravity, the effect of ordinary gravity, by just adding 1 to all of these to cancel out the -1 in front. All right, and now you get this because I'm not concerned about the gravity. I only want to measure the velocity due to the motion of the elevator, not due to ordinary gravity. All right, so these are the same numbers, but I just took away 1. And then I converted the units. These are in G's, remember? I convert that to feet per second squared, which is these now. All right, and then right here, total velocity change. You can see the formula here. What I did was I added these up. The sum from P2, which is this one, this one here, P2, down to P21, which is that one, right? I did not include P22. That's because I'm trying to do the rectangle sum on the left endpoints, all right? And then multiply by M22 minus M2, which is that, divided by the count. This is the B minus A over N, right? The B is this final time. The A is this original time, divided by N is that much. All right. Anyway, this should be the value of the integral. That is to say, this is how much my velocity changed in total during this little burst of acceleration. Since I started out at rest, that means this number is the velocity that the elevator was moving while it was going from one floor to the next. In feet per second, 1.3 feet per second, not very fast. Just for fun, I converted that to miles per hour. 0.89 miles per hour. Again, not terribly fast, but it's kind of cool, I think, that you can actually do this, measure how fast the elevator is going. Of course, a much easier way to measure is just measure how tall one story is, and then measure the time it takes you to get from one to the next. You should get a number that's pretty much the same as this one. All right, that'll do it.